This is a video for AQA Further Pure Mathematics, Numerical Methods, section 2.2, where we're looking at solving differential equations using the midpoint formula. In a previous video, we looked at Euler's method for approximating the solution to differential equations, and that used the idea of the gradient of the function at the beginning of an interval, and using the approximation that we could use a straight line across the interval instead of the curve to give us the value of y1 and then successively y2, etc. The Euler's formula was given by this equation here, where we say that the next y value is equal to the y value that we know yr plus h times f of xr and yr. Now h is the size of the interval and f is the function of x and y, which is going to be able to allow us to evaluate the derivative or the gradient at any given point. Now the idea of using the gradient at the beginning of the interval is very straightforward. However, there are other methods that we can use which lead to less error in the calculations and therefore give us better approximations. This diagram shows that the gradient at the midpoint of an interval here is going to be approximately the same as the gradient of the line between the endpoints of an interval. Therefore, we can use the idea that the gradient at that midpoint, which will be given by the function, remember, which gives us the derivative, so f of xr yr, that will be approximately the same as the gradient using this triangle. Now the height of the triangle will be yr plus 1 minus yr minus 1. So that's from the start point to the end point, divided by the length of the interval. Now this time the length of the interval is going to be 2h. And that then can be rearranged to show that the value of yr plus 1 is equal to yr minus 1 plus 2h multiplied by the gradient at that midpoint, f of xr yr. Now, of course, to use this, we need to know two values. We need not just one value to work out the next one, but we need the previous 2 points to work out the next one. So to work out r plus 1, we need r minus 1 and obviously the value at r. So there's the reason again. This is the midpoint formula, which says that the next value, r plus 1, is the value before the point that we are at the moment, r, and then plus 2h times the gradient at that midpoint. Now if we've only got one point, which is quite usual, we only know y0, the first point, then we can work out a second point by using Euler's method as in previous videos. So that then gives us 2 points, the first one using a known point and then the second one calculated from Euler's method. But once we've got those 2 points, we can then proceed with this improved formula, the midpoint formula, for all the subsequent values that we need. So let's look at that in practice with an example. In the previous video we saw that if we had this particular differential equation here, where dy by dx was x plus root y, and we had a known point x0, y0 at 1, 1, then Euler's method gave us the second point x1, y1 as being 1.1 and 1.2. Now that was using the idea of the gradient at the start of the interval. But now using the midpoint formula, we can work out the second point, which will be x2, y2, but this time using the gradient of the line at the middle of our interval between x0 and x2. In other words, the gradient at this point here, but we're going to go from y0 to y2. So using the formula, we can see that y2 will be equal to y0 plus 2h and then f of x1 and y1. If we put in the values that we know, then we know that y0 is equal to 1, and then we've got 2 times h, so that's 2 times 0.1, and then the value of the gradient at 1.1 and 1.2 is 1.1 plus the square root of 1.2. And if you evaluate that, you'll get a value of 1.4391 to 4 decimal places. So Euler's method was used to find this first point at x1, y1, and then we're going to use the gradient at that point, which would be something like this, for example. Now Euler's method, if we continue it, would give us a point here, but instead of using that gradient starting at x1, we've used the gradient starting at x0, so we're going along this line to give us this point. So you can see in general this is going to be a better value as an approximation than Euler's method would give. So the formula that we need then is this midpoint formula, which says that yr plus 1, the next value, is using the value before our midpoint plus twice the interval 2h multiplied by the gradient at the midpoint. Now in exam questions you'll probably be asked to do this once, usually asked to find x1, y1 using Euler's formula, and then to find x2, y2 using the midpoint formula. However, as with all of these methods, these are very easily computerized or can be done on spreadsheets. And that means that we can vastly increase the accuracy as well by reducing the size of the interval. Well, that completes this video on midpoint formula. In the final one of this series, we'll be looking at an improved Euler's method, which again is a method which is designed to reduce the errors in the calculations.